What's up, everybody? It's Mr. Hines. We are going to do some fun with polynomials and talking about their characteristics. And I wanted to start with this separate sheet that I gave you, starting with number 24. We found the volume of a cylinder, and this is when we were just building out polynomial functions. And so I gave you the equation again for the volume of a cylinder. It's pi times the radius, which is 6 minus x squared, times the height, which is x plus 2. And so here is a polynomial that has multiplicity. It has 3 zeros, and we are going to graph that. So we are going to use a calculator to graph it, but I think that one of the zeros should be at -2 because of this linear factor here, and this other linear factor gives me 1, 2, 3, 4, 5, 6 as the other zero. Now the rest of it, we'll let the calculator flesh this out for us. Notice it says the y-axis is going by 50 here. So here's what I'm going to do. Pi 6 minus x squared times x plus 2. So writing it just the same way. It didn't have to multiply it out or anything. Just writing it in there. I need to change my window. I'm going to make -5 be the bottom. That was just like an arbitrary choice. And the top, let's see. We're going by 50s, right? 50, 100, 152, 300. That way it will match pretty well on the graph that we see here. Okay, so we want to put this graph on that. So there's a few critical points that I am interested in. So one of the things it's going to ask us for is the maximum. And so I'm going to go ahead and find that so that I can make my graph be a little more accurate. First of all, I'm going to go to the table. I see when x equals 0, y is 226. So 50, 100, 200 is right here, 226, about right there. So the function starts down here, goes up through that point. We're going to find the rest. We want to find that maximum point. We're going to hit second and trace, where all the good stuff is in the graph world. We want to find a maximum. So that's number 4. It says left bound, and we already are on the left side of that 0. So we hit enter. Zoom over to the right side of it, hit enter a third time, and it tells us this is about 2/3. The y value is 238. So let's see. 6, 7, 238. Is that what I said? I forget what I say sometimes. 238. So let's see. That is right about here. So we're going to go up through that point and then down and then right back up. Okay. And so if you're wondering how do I know that it doesn't go back underneath the line, because we have multiplicity on that 0. So because there's multiplicity there, I know we don't go below the line. That kind of has to do with part C. So I want to start, I want to do that one now. So on part C, make this video smaller. On what intervals it's positive and negative. You know, that has to do with the zeros. Not just a little bit, a lot of it. So one of the zeros is -2, the other one is +6. We can just take each factor, set it equal to 0 and solve, and we find that out. And then we can just try a point from each little section. So something less than -2. I'll try -4. So if we plug this in, 6 minus -4, that's a positive number, and it's squared. So it's still going to be, we'll have positive. And then if I put -4 in here, -4 plus 2, that's negative. So I'm going to have a positive number multiplied by a negative number. That means that that interval is negative. So from -∞ to -2, that is a negative interval. And then you can probably guess that it's going to be positive. So if we plugged in another number from there, we would see that we would have a positive squared times a positive. And then the last one would be to take a point after 6. So, I mean, you can take any number beyond 6. I'll take 8. 6 minus 8 would give me negative 2, but then it's squared, so it becomes a positive. And then if I use 8 here, 8 plus 2 is also positive. So a positive times a positive is positive. So from 6 to infinity, it is positive as well. So this is kind of unique in that it's a negative interval, then a positive, then a positive. And the reason that happens, the reason you have back-to-back positive intervals is because there's multiplicity at that 0. We also want to know on what intervals. So let's see, this is at 238. This function increases and decreases. So we have to know our minimums and maximums in order to be able to tell where this stops increasing and starts decreasing. So the definition of a maximum is a point where a function stops increasing, starts decreasing, and a minimum is just the opposite. So this function, if you were coming in from the left, you were on a roller coaster, you would be going in the upward direction, your height would be increasing. So increasing, this function does that from negative infinity, so all the way from the left side coming in, it's going up, 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 until it gets to this point right here. I'll do 0.667. And then at that point, it starts to decrease again. So once it hits the maximum point, begin going down, and you decrease until you get to 6. Why 6? Why not 0? Because it's the x values. Anytime you see intervals, x values. If you have to, you can just erase the y values on your paper. Only use the x value numbers. So you see we start at negative infinity, then we go to this one, and then we go to this one, and then we go to infinity. Those are the only numbers that you should see in your intervals. So once we get to 6, we stop decreasing and we start increasing. We never stop increasing after that. So there's our intervals increasing and decreasing. What's the maximum volume of the can that you designed? So that's this number right here. How do I know that? That's what we got to know. So the volume is equal to all of this. So those are our y values. The y-axis is volume, the height on the graph. The x has to do with some amount, some number of centimeters that we are maybe like cutting out of one piece and adding to another piece. And so if you think about it, it makes total sense that if you have a radius of 6 minus x, if you take away 6 from, if x was 6, then what's your radius now? 0. And so you see down here that the volume becomes 0 at that point. So the more you cut out, the skinnier that can becomes, and the volume eventually is 0. Then the crazy thing is that this is the maximum point. So the most effective, like you cut a little bit out and you add it to the other side, the height, and you actually gain volume up to a point, and then it starts to become counterproductive and you start to lose. So this is why a function like this might be beneficial, because you can see the relationship between the two and learn how to maximize the situation. And now you're saying, okay, but that's not the absolute maximum. It goes up higher over here. Okay, but what is that then? That is where you are taking away, maybe if like when x equals 8, you have a radius then of -2. That does not make any sense at all. And so what can x not be? That has to do with the domain. The domain, x has to be greater than 0, but less than 6. Okay? So we're only looking at a very narrow spot in there. That's part D. For what values of x can you have a volume greater than 100? Create a table to show where the solutions lie. Indicate the location of the solutions on the graph from part A. So what I'm going to do is draw a graph of 100. And so you can see when x is 0, we're still above that 100 line. until this point right here. And that's what we want to know. We want to know, when does this thing stop being above 100? So for that, you can do a couple things. You could graph 100 on y2. So now it looks just like the function we have. I don't know if you can hear this on the video, but that is ice hitting the window. Probably need to go home. And then you can do second trace, and we can find out where those points intersect, or our calculator can for us. You just need to move the cursor over in that direction and then hit enter 3 times, and it tells you intersection 3.6, 100. 3.6. Okay, so from x equals 0, x is greater than 0 to less than 3.6. That's a less than sign, sorry. This will have a volume greater than 100. Once you cut more than that, you start to be below 100 cubic centimeters. Creating a table, you can literally just transfer your table from here, starting with 0 to 26. So this is x, this is volume. When we get to 1, 235. And you could even make this go by 0.5s to be a little more accurate. Hit plus, the plus sign, and 0.5, and now your table will go by 0.5s. You don't have to though. So we'll do 2, 201, 3, 147. So all these numbers, you see the volumes are greater than 100. And then when we get to 4, it says the volume is 75.4. 75.4. So what I'm going to do is draw a line and show, okay, so somewhere in here, we want values from that are somewhere in between 3 and 4, all the way down to 0. And we can have a volume greater than 100. This problem, I would say, is the toughest one on any of the sheets, just because there's so much context. But I do want to try to give you guys some context of when you might use a polynomial, what you might use it for, how it fits into, how what we're learning might fit into a real situation. And with that, we'll jump to the next one. Okay, the next ones I think are faster, and we should knock them out pretty quick. All right, next up, baseball. We've talked about cans, now we're talking about baseball. It tells us that there is a function that can model the height. Okay, so what do functions do? They connect 2 different variables and show how they're related. So in this case, the height is related to how much time has passed since the ball was hit. Says, which of the following are correct statements about the baseball after 4 seconds? So here's what I'm going to do. I'm going to find 4 seconds, go up on the graph to that point. This is the moment that we are looking for. We want to find out which of these statements work. The ball has traveled over 140 feet. Okay, so from where it left the bat to here, has it traveled 140 feet? Okay, horizontally, we don't know. This is only telling us about the height. So let's look at the height. It started at 0. Then where did it get to? It got up over 140 feet. Well, how did it do that? It has to travel at least 140. And now it's traveling back down. So it's even traveled further than that, more like 150. So I'm going to say, yes, it has traveled 140 feet at least. The ball will hit the ground in a little more than 3 seconds. So from this moment, when will it hit the ground? 1 second, 2 seconds, just a little over 2 seconds, not 3. If it says a little more than 2, I would be on board. Should say 2. So that one's not true. The ball has traveled over half its total flight time. Okay, well, where does it hit the ground? Here's the ground. Ball goes up off the ground, gets to its highest spot, comes back down. So 6 seconds, half of that is 3. 4 is bigger than that. So yep. And the ball is on its way back down to the ground. It is, in fact, on its way back down to the ground. So there's that one. Cookies are cool, this should be over here. This point is a absolute maximum. But I think that this is a super cool graph. I'm not even going to answer the question. But as you look at profit versus price, if you don't charge anything, you're not making any money. If you charge too much, you're not making any money because nobody's going to buy your cookie for $3.50. The sweet spot is where you're charging enough that people will still pay for it, and you're selling a lot of them. So each cookie you're making as much as you can off of while still selling a lot of cookies. So that's the relationship that's showing. So even something as simple as cookies could pay off in this situation. Polynomials. Number 27, see I've already got it circled. But if you would just take these numbers and sketch a basic graph of time and the height over here, then you would see something that goes up like this. And you would be able to make your prediction about when this thing's coming down. We see that at this point right here, it's at a maximum. Okay? So it's the highest it ever gets. And I know that because it's even on either side. So I know that that's the very top, the very peak. And then it goes down, back down, hits the ground in 10 seconds. This one, I hope that you can do. The answer is on, it's on the Google Doc in the comment. So if you want to see the answer, make sure you get that one right. But the zeros, just the only thing to really be careful of is that there's multiplicity on that particular zero. So that changes how it acts when it hits the x-axis. And last one on this page, lucky number 29. What's true about the graph of the function once you factor and rewrite the function? So how can we factor that? If they're going to ask us about factors, let's try to factor it first and then we can compare. So your first question, what do you look for? What do you look for your first thing to factor? Hopefully you're thinking GCFs. So the GCF of this thing is x. I can divide both of those by x, and I get x squared minus 1. I see that here. And we could find the zeros from that. So you get x equals 0, which it tells us is true. And what do we get from this one? X squared minus 1 equals 0. That means x squared equals 1. Square root of both sides, and we get x equals what? What's the square root of 1? It's 1. So is this correct? Almost. You get plus or minus 1 as your solutions for that. So 1, yes, but also we need negative 1. So I think that there's probably a better option for this. But another thing that I learned, when you find these solutions, positive and negative 1, that should be a hint to you that that quadratic you were just looking at factors. It's actually the difference of two perfect squares, so it factors in a specific way. But if the solutions are x equals 1 and x equals negative 1, we could actually kind of work backwards and find out the two linear factors that would have given us those solutions. Subtract 1 from both sides. You get x minus 1 equals 0 and x plus 1 equals 0. So this factors into x minus 1 times x plus 1. There's actually 3 zeros. So you can find the zero of the function to be x equals 1, but it doesn't say anything about 0 or negative 1. So it's not that one. So get B. The x-intercepts 0, 1, and negative 1. Awesome. Factoring it, boom. Letter B. The last thing I want to do in this video is go through two of the problems from the last page. Let's look at number 22 and let's look at number 18. Okay, we'll do 22 first, it's quick, and then we'll talk characteristics on number 18. So the thing that we're trying to do with 22 says determine which intervals it's positive and negative. So this has to do with characteristics of the graph and what the graph is going to look like. But instead of looking at the picture, we're looking at the function that gives us that picture. So the one thing that you need to find is you need to find the zeros, okay? Because we've talked about with a function, if it goes like this, then the zeros are these points right here. those are the only place where you can go from the positive region, which is anything up above the x-axis, to the negative region. So those are your crossover points where you start in the negative maybe, and then you go to the positive side. And then how can you get back to the negative side? You have to go through a 0. So for us, we want to know where those zeros are. And one of them is at x equals 4. Now, where are the other ones? If we wanted to factor this, we would do 1 times 16. And we'd say, what are factors of 16 that add up to 4? And the answer is just sadness. So there are no factors that will do that for us. So what we're going to do is use the quadratic formula. We've got negative 4 plus or minus the square root of, let me erase that. Yeah, 4 squared minus 4 times a times c over 2a. So negative 4 plus or minus the square root of, I think this is negative 48 over 2. And I'm not even going to finish it because this negative sign right here says that my solutions are going to be imaginary or complex numbers. So complex numbers don't show up on the x-axis. And what that means is the function doesn't actually look like this. The function probably looks a little more like this. So it goes through the x-axis at 4, but it doesn't go through anywhere else. So the potentials would be that or something maybe more like this, where that's the only place it's crossing from positive to negative. So you're going to create a number line, and on that number line, 4 is the only dividing point between positive interval and negative interval. And what we'll do with it is you just try one number on each side. So that means there's 2 regions for this one. There's this side where it's either positive or negative. And then on this side, it's either positive or negative. There's only 2 possibilities for this function. And you can just take any old number that's less than 4 and take it from a seasoned veteran. We're going to use 0 if we can. So 0 is less than 4, right? 0 minus 4, that's a negative number. And it's going to be multiplied by 0 squared plus 0 plus 16. That is a positive number. What's a negative times a positive? Negative. So this region, the function is negative. So it's kind of like this one down here. So it's negative. And then we want to check and see, like, hey, does it actually cross that axis there? And for that, we're going to plug in a number that's greater than 4. How about 5? So if I plug in 5 in all these places, 5 minus 4, that's a positive number. 5 squared plus 20 plus 20, that's a very positive number. So this one's positive. That kind of looks like a face. So this region, it's positive. So let's write our negative interval from negative infinity to 4 and our positive interval from 4 to infinity. All right, last one. It's a doozy. We've got a function here. It is a cubic function, and we want to know all the things that we can know about it. The last one is, well, the last 2 is actually where I'm going to start. Because that kind of reveals a whole lot about this function. List the x-intercepts. So x equals, let's go back over here. We've got -3, -1, and 2. -3, -1, and 2. Those are all our x-intercepts. And so what does that do? Well, it helps us write out the polynomial, or at least get a really good idea of what it is. X plus 3 comes from this one, x plus 1, and x minus 2. That is the function rule, or at least it's close to it. You don't have to multiply all that out, especially because right now, the way we have it, it's wrong. The reason I know it's wrong is because of the way this end points. So what should the leading coefficient be, class? It should be negative, okay? Crosses through at +3. Where would ours cross through? What's 3 times 1? 3 times -2 is -6. So there needs to be a negative number out here or a negative out here to make this thing turn upside down, because right now it's going to end in the positive direction. Negative sign will fix that. And it actually probably needs a 1/2. Okay. We haven't talked about adding that to our graph, but maybe something like that. So that's the function rule. The zeros are what I want to cue in on, because that helps us with the intervals positive and negative. So think about the x-axis as like all the pages in a book. They start at negative infinity and they end at positive infinity. And we want to know from negative infinity to positive infinity, where's the markers between positive intervals and negative. So this thing starts off, the first thing we see, where is it? It's in the positive region. So starting at negative infinity, it's in the positive region until it gets to that first 0, -3. And then at that point, it goes from -3 to -1, that's down here, and it's negative. And then the next value at -1 goes back into the positive region and stays positive until 2. And what I want you to notice at this point is that every number I'm writing is an x value from this group. The last one, it's negative from 2 to infinity. So you got your bookends, you got the infinity signs, and then everything else is one of the zeros in between there. Getting close. Let's do domain and range right quick. Domain, all reals, because it's a polynomial. The range goes down to negative infinity over here, goes up to positive infinity over here, hits everything in between, all reals, all y values and all x values. Go get them somewhere. Then we want to do intervals increasing and decreasing, which means we need to know the maximums and minimums. Okay. First question, are they relative or are they absolute? And I hope that you said that they're relative, because the function, this is that's my maximum, that's my minimum. The function does go above that point and it does go below this point. So that's what makes them relative, is that they're not always the highest and lowest, but in that little area. That's why they also call them local maximums and minimums. In that area, they are the highest and lowest. You could take your function and graph it and get the maximum and minimum from there, but I'm not asking you to on these because of this little -1/2 that changes absolutely everything. If you don't have that in there, you won't have the right maximum minimums. So we're just going to eyeball them. This one, x is -2, the y value is about -2. And then this one over here, it's about 1,4. So really just being very basic with it. So we've got a relative maximum at 1,4. We've got a relative minimum at -2, -2. And that helps us do intervals increasing and decreasing. So let's go back up here. And if we're doing an interval, I want you to erase the y values. Get rid of them, because they'll only bring you heartache. We only want the x values. So what's happening to our function as we come in from -infinity? We're on the polynomial roller coaster and we are going down. Our height would be decreasing at first. And it decreases until we hit that first minimum point at -2. By the way, that is the definition of a minimum point, is where a function stops decreasing and starts increasing. And so that's what we're indicating here. It decreased until that minimum point, and then it started to increase. Well, where does it stop increasing? Ding, 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 at the maximum point when x equals 1. And then it starts to decrease again from 1 until infinity. And that's it. If you have questions, I encourage you, let me know. I would love to answer them. Love to help you out as you get prepared for some polynomials.